Hi everyone. In continuation with our series of lectures on the different sources of participation in a CMOS inverter, in this lecture we will look at another important source of participation, which is the leakage power consumption. Now first we will look at what are the sources of leakage in a CMOS inverter, and then mainly in fact we will focus on the diode leakage, which I'll be talking about in a few moments, and towards the end I'll talk about another leakage which is called the gate leakage in a CMOS inverter, and under what conditions or what are the paths for the current from supply to the output node or to ground in such cases. So to first understand the leakage current, we'll have to just briefly look at the device structure of a MOS device. So you have shown here is an NMOS device. So same thing will hold true for a P-channel device as well. So you have source and bulk. So typically your bulk is P substrate and source and drain region are N plus diffusion regions. So they naturally form a PN junction. And we'll always ensure, if you remember, bulk is always tied to the lowest potential possible. Okay, so that's the one obvious reason, is to ensure that the drain to bulk and the source to bulk PN junctions are not forward biased. So we have to ensure that condition, so it's always connected to the lowest potential possible. Now, a diode, when it is conducting in forward, if the diode is forward biased, then its current will increase exponentially with the voltage across it. But since we are never going to keep any of these diodes, the parasitic diodes that get naturally formed in the structure of a MOS device, we are never going to turn that on. We can ignore the forward bias operation. We are always going to keep it in reverse bias region. So for a diode, if you have 0 volts across a diode, only then you get 0 current across it. Otherwise, you'll always have, if you have a finite reverse bias voltage, you'll always end up having a finite current called the reverse saturation current flowing through it. I'll share a very interesting exercise, very interesting problem, which I remember almost 7-8 years ago when I was working for another company where I was designing synthesizers for WLAN and mainly for WLAN and for cell-based applications. There was another team which was building analog BLE transmitters. So eventually, today, most of the BLE transmitters, Bluetooth transmitters, are all digitized now. But at that time, there was a very promising solution which used a technique called open loop modulation, which is you have an oscillator. So generally, we need a PLL to set its frequency. But PLL was a power consuming block. So Bluetooth means it's a very low power system. So you'd want the oscillator to operate in open loop. So what you do is we would let a PLL lock and figure out what the control voltage is, and then we will let the oscillator open. Okay, it will just be running in open loop. And this is an idea many companies were exploring at that time. So what you need to do is you need to store an analog voltage onto a capacitor and then hope that this capacitor voltage remains nearly constant, so that within the duration of data transmission, the frequency also remains more or less the same. Okay, so there are of course some specifications as to how much the frequency can drift, etc. But let's not focus on that. The problem that engineers that they were dealing with at that time was that how to keep this voltage across the capacitor constant. So to keep the voltage across the capacitor constant, because it's a CMOS IC, so you will have somewhere you will end up having some diodes. Okay, either you put a switch or there is some device that is it's connecting to that node will end up having some parasitic diode, unwanted diode naturally formed. And if you have this diode, the diode's leakage current, even though it's cut off, it's in reverse bias, that might discharge this capacitor. So to ensure that doesn't happen, the designers had to ensure that the voltage, most of the diodes had 0 volts across them. And of course, that how they did that was again a company secret, but it's a very interesting problem. So I thought to discuss that. To ensure that there are no leakages, you need to ensure that the voltage across the diode is nearly 0. Okay, then you get a 0, and 0, not nearly. It has to be 0 so that the diode current will be 0. If you apply a reverse bias voltage or even a finite forward bias voltage, you will have some current flowing in the diode. Okay, so this is the IV characteristic of a PN junction diode, and mostly we will be operating in this region. So which means there will be some constant leakage current flowing in the diode. For a range of voltages. Now, of course, a diode usually when it breaks down, then you end up having a sudden surge of current. But we'll assume that we are not breaking this diode, so which means there is only a constant leakage current or the reverse saturation current that's going to flow in this diode. If you look at a CMOS inverter, of course, you have one diode from source to bulk. Okay, and similarly, I can also think of I can show you an N-channel device. If you quickly draw out an N-channel device, I can probably show you briefly. In place of a P substrate, you're going to have an N substrate and P plus and source and drain diffusion regions. And in this case, the diode is going to be this way. So you'd have source and drain terminals or the anodes, and the substrate will be your cathode. So that's why we normally hold the N region at the highest potential possible. So this diode is also reverse biased. So you will have two diodes. So this is the diode corresponding to drain to bulk. Similarly, for NMOS, this diode corresponds to drain to bulk. Source to bulk diodes, the voltage across them is 0 because they get shorted out, because I've tied source and bulk together for this PMOS, source and bulk together for this NMOS. They both are at the same potential. So I can ignore the other two diodes. The source to bulk diodes can be ignored both in a CMOS inverter structure. I can ignore the source to bulk diodes. So now the next thing is what does these diodes depend upon? They depend upon the diffusion width. They depend upon the diffusion depth. They also depend upon the width of the diffusion region, and also the width of the MOS device itself. So I've just cut out the N plus diffusion region here. So I've just shown a cross section here. Okay, so it depends upon, let's call this as T as this dimension. The diode will depend upon the area of cross section of this diode will depend upon the device width and also the width here. And there are techniques how to estimate this diode's capacitance very accurately using some simple geometric approximations. Most courses on basic digital VLSI design would cover that. Most textbooks have that. So you can find you have a PN junction diode forming this way, on this side. So on all the faces of this MOS device except the top face, and if the channel is conducting, you ignore the other phase as well. And on all the other phases, you'll end up getting a diode structure. So you can estimate what is the total total area of the diode. Okay, so which helps in estimating the reverse saturation currents. So we don't care about that now. So mainly I'm looking at just to give you a feel for what this leakage current depends on. So to understand what is the leakage current parts, that's the next goal. So we'll assume the input is 0 first. If I assume the input is 0, NMOS is cut off, and your PMOS will charge the output node voltage. I have shown NMOS here is cut off, so I'm ignoring it. PMOS charges this output capacitance to VDD. So now if you see, even though NMOS device is cut off, the drain to bulk junction diode is active. I mean, it's in reverse bias. It's biased in reverse region with a reverse voltage of VDD in the steady state. Okay, so it gets charged to VDD through PMOS. And if you see, since this node voltage is at VDD, the drain to bulk diode, due to the PMOS, will not be carrying any current because that has a VDS of 0, because the drain voltage is 0, source voltage is at 0. So this diode will be not carrying any current. But the lower diode, which is the NMOS diode, will carry a leakage current. So I'll ignore the diode, drain to bulk diode of the PMOS. So this is what the structure reduces to. Once this node is charged to VDD, close to VDD, then you will have a leakage current flowing from the supply through this PMOS to ground. Okay. Similarly, when the input is VDD, if you apply the input to be VDD, I've ignored the PMOS because the PMOS is in cutoff region. So its VGS is less than VT, so we can ignore the PMOS. And we will look at the output voltage will eventually be discharged to 0 volts. So which means the drain to bulk diode of NMOS will not carry any current because it's 0, the leakage current is 0. So the drain to bulk diode of NMOS will not carry any current. But the Diode of the PMOS device will see an entire VDD reverse voltage across it. So source is at VDD, drain is at source and bulk are at VDD, and the drain is at 0 volts. So the drain to bulk voltage will be VDD. So you'll have a reverse saturation current flowing from the diode through this NMOS device. Now if you notice this, if your input level is 0, you have a leakage current flowing through the PMOS device, and this leakage current is determined by, this is your input clock signal. This leakage current is determined by the diode, NMOS diode, so I'll call it I leak N, and when the input clock signal is high, the leakage current is determined by the PMOS diode, drain to bulk PMOS diode, so I leak P. And if I assume I leak N and I leak P are same, or if I don't assume, then the average current drawn from the supply. So when input is 0, you're drawing I leak N, input is 1, you're drawing I leak P, average current is the average of the two currents. I mean, you take the summed average, arithmetic mean, you get I leak P plus I leak N by 2. Okay, times VDD will be your leakage power dissipation. Okay, so if your duty cycle out, I mean, if you have a finite duty cycle, then you can write I leak N into the on time. So whenever you have high, whenever your clock signal is high, then it will be, it's I leak P. Okay, so I leak P times D plus I leak N times 1 minus D will be the average current that you're going to draw from the supply. Times VDD will be your leakage power consumption. If you assume the NMOS leakage and PMOS leakage currents to be exactly same, then you will always be drawing a current of value I leak from the supply, where I leak equals the PMOS or the NMOS leakage currents. Okay, so this is the source of leakage in a CMOS inverter, which is mainly the diode leakage. And if you see, look at this current, this is independent of frequency. It doesn't depend upon frequency, it doesn't depend upon the load capacitance, and it has a linear dependence on the supply voltage. So if I increase the supply linearly, because I leak remains more or less constant. If you look at the diode characteristics, it was more or less constant even if your voltage across it was changing. So that remains constant. So your output voltage, if your supply voltage increases linearly, then the leakage current will also increase linearly. But the important thing when we talk about leakage is temperature. When you increase temperature, so if you recall any basic study from any device's course, your leakage currents the reverse saturation currents will depend upon the intrinsic or the minority carrier intrinsic carrier concentrations, and the intrinsic carrier concentration will just exponentially rise with increasing temperature. Okay, so I'll probably discuss this on a course on devices, but any textbook on basic device physics will tell you that if you increase your temperature, your intrinsic carrier concentration will increase, and that will also increase your reverse saturation current. So your reverse saturation current in a diode will increase exponentially with temperature. So leakage currents will shoot up exponentially at high temperatures. So that is something you will see as you increase the temperature, you will see the power in an inverter will increase. It could be a combination of many things. I didn't talk about it in the last lecture on when I was talking about short circuit participation, but even short circuit participation will increase with temperature. So I'll probably, when I'm closing the discussion, I'll comment on all those points. But here we see that the leakage current increases with supply linearly. Okay, it doesn't depend upon clock and load capacitance. So this was the question I posed in the first lecture when we talked about the power dissipation as CMOS inverter. I said that even though you change the clock frequency, the power dissipation remained the same. And that means the leakage power is the dominant source of power in that example. So leakage power is almost like a DC power or a class A power. This leakage current is constantly flowing from the supply, even though your input is changing from 0 to 1 and so on. Okay, it's always drawn either through PMOS drain to bulk diode to ground or through NMOS's drain to bulk diode. Okay, so that's the diode leakage current. The other source of leakage, which is very prevalent in lower technology nodes, is the gate leakage. So this is the leakage current. So this happens due to a phenomenon called quantum mechanical tunneling. Again, any basic devices course will talk about that. So we'll not talk much about that right now. But we should understand what is the path for the gate leakage current. So let's assume you have two inverters. To understand that, you should assume not just from a single inverter, it's difficult to understand it. Understand you have two inverters, and the first inverter's input is 0. Of course, the final output of this inverter will also be 0. So you have cascaded two inverters. So if you apply 0 here, you get 0 here as well. This output will be charged to VDD. So there is a leakage current, diode leakage current flowing here directly through this. The other leakage that we need to be concerned about is the gate leakage. So when you have a VGS and drain to source are nearly at ground, your drain to source is nearly at ground, you'll have a leakage current flowing through this NMOS device. Okay, because it has a large VGS. Okay, and so this happens due to quantum mechanical tunneling. And when you have a large VGS, you'll have some electrons escape from this point to the drain. It will tunnel through from gate to your drain and source regions. Okay, so again, there are very good explanations for that in many books. You can refer to that. Any book on standard device physics will talk about that. So that's the source of your gate leakage. So gate leakage depends upon the oxide thickness. With lower technology nodes, your oxide thickness is decreasing, so it will also keep increasing. The other important thing that the gate leakage depends upon is the exponential dependence on VGS. After you increase your VGS to a certain point, then which is greater than VTH, your gate leakage will increase exponentially. Okay, so whereas a diode leakage did not change much with the VGS or the VDD, but your gate leakage will have a very strong dependence on VDD. Okay, so when you are increasing VDD, you should expect, if you have gate leakage as a dominant source of participation, it should increase exponentially as well. So to complete the discussion, the other part of the gate leakage is if I'm applying VDD. Let's say I apply VDD, then I would expect the output to go to VDD, and this PMOS device is fully conducting. So for gate leakage to take place, you need to have a finite VGS. Zero VGS will not lead to a gate leakage. So you need to have a finite VGS. So that's why I did not consider a PMOS for gate leakage in the previous in this example. But in the other case, when you apply input as VDD, output is supposed to be VDD. Okay, the input of the first inverter is 0, so NMOS is cut off, so I can ignore the NMOS device here. The path for leakage will be through the PMOS device through gate and to ground, through this NMOS device to ground. So that will be the path for leakage of this, in this case involving CMOS inverters. Okay, so even here, when the input is 0 and 1, I can approximately argue that the power dissipation will be proportional to VDD times IG leak, the gate leak. Okay, the gate leakage current, and this gate leakage current, mind you, has a dependence on VDD. If you increase your VDD, it will increase exponentially. So the gate leakage will be an exponential dependence, and it also depends on temperature. Again, any leakage phenomenon will depend on temperature. So it also depends upon the thickness of the gate. So if you're smaller thickness, the gate leakage will be quite high. Okay, so that's the point about leakage currents and leakage participation in a CMOS inverter. Okay, so the two sources, you have a diode leakage, which doesn't depend much upon the VDD, but gate leakage has a strong dependence on the gate to source voltage, which happens to be the VDD of this digital circuit. Okay, so leakage power does not depend upon clock frequency, and it also doesn't depend upon the load capacitance. Okay, it may have some second order dependence because load capacitance, if you involve parasitics, will be a function of how big the device is. So that might determine some, diode sizes. But if I explicitly put a cap on the load, I can say that it doesn't depend upon an explicit additional cap you add on the load. Okay, and it doesn't depend upon the clock frequency, so it only depends upon temperature, and in case of and also the doping concentrations for a diode leakage. And in case of gate leakage, it depends upon the voltage as well. It has an exponential dependence on the supply as well. So that completes our discussion on the different sources of participation in a CMOS inverter. So you have dynamic participation, which depends upon the load capacitance, supply, and clock. And then we have the short circuit participation. I've written this expression in terms of slope, but you can also write it as alpha times TR times I peak into VDD into F clock. Okay, so it can also be written in terms of the rise time. So if your slope is infinity, rise time is 0. So this short circuit power dissipation, the other important source of power, depends entirely on the slope of the input signal. It depends on the shape of the input waveform, whereas the dynamic power dissipation does not depend on the shape of the input waveform. Okay, so it purely comes from charging and discharging of the capacitor. So that's the source of dynamic power. Short circuit power depends upon the finite rise times or the finite slope. The slope is infinity, it's 0. And also it also depends upon the clock frequency, how frequently you're extracting charge out of the supply. So it depends upon that. And every time there is a transition, there will be a short circuit power dissipation. This is the power that dissipates only during the transitions. Okay, so when the input is constant, you don't see a short circuit power dissipation. The third one is the leakage power, which has no dependence on clock frequency. Okay, it has no dependence on the clock frequency or the load capacitance to a first order. But if you assume diode leakage, it's directly proportional to VDD. And if you assume a gate leakage is the dominant source of leakage currents, then that will have an exponential dependence on the supply. And leakage currents will have the worst increase with temperature. So when you increase the temperature, your leakage current, whether it's gate leakage or diode leakage, they will just increase exponentially with temperature. Okay. The other term, which is the short circuit power, also has a dependence on temperature. That dependence comes from this peak current. So this peak current, if you recall from one of the previous lectures, depends upon beta n VDD by 2 minus VTN the whole square. So if the increasing temperature, beta n depends upon mobility, this term will decrease, but your VT will also decrease. So you'll always have a combination of both. Generally, what I observe in low voltage digital devices is that the effect of VTN always dominates. So when you increase the temperature, I normally see an increase in the short circuit currents. Okay, so that completes our discussion on short circuit power dissipation. It's very good to know that on what different parameters does the power dissipation in a CMOS inverter depend upon. So hope it was helpful. Thank you.